Morning, everybody. Happy Monday. No? What's worse is next Monday will be the day after the time change. So that makes today better, right? So yeah, this is good. Fall back, spring ahead, spring forward, fall back. So that means you lose an hour of sleep this coming Saturday evening. Let's see. Complain to Congress, please. Let's see. Test. Oh, good. You have the exam before the time change. Okay. So exam this Thursday. What are we doing on Wednesday? Review, right? What does review mean in this class? You come and ask me questions, right? It's really your day to tidy up everything. So I did post the exam topics, right? Did that. Today, we're going to take that field trip, but we're going to kind of change it up a little bit because the place is still not good. So we'll do the next best place, which isn't that great. And then I've got a couple more examples of conservation of energy, just sort of kind of tying everything together with work other and all that sort of stuff. So we'll try and get all that done today and review on Wednesday. All right. So this long promised field trip, which I'm sure has been hyped up in your brains and you think it's something fantastic, it's not. But this goes back to power, right? And just as a reminder, this is kind of from chapter 7-ish stuff, but it still applies, okay? What was power? Mechanical power? Work over time, right? It's work or energy expended divided by a time. So this is capturing, right, that energy in time. And the more energy you expend in a shorter amount of time, the greater your power output is going to be. So units for power in SI units, do you remember? It's a watt, right? And there's another unit called the horsepower, which I think I told you about a little bit, right? 1 horsepower is equivalent to 746 watts, okay? Which is also equal to 550 foot-pounds per second. So the horsepower and the foot-pound per second really are not standard units. The SI unit would be watts. But the question that I'm going to put to you, and the reason for our field trip today, is this. Are human beings capable of 1 horsepower worth of output? No? Yeah. Slow opinion of human beings, right? Yes? Okay. So how do we find out? What does a human being need to be able to do to achieve 1 horsepower? What? Pull a cart? Okay. So if we had a 550-pound cart, right? We just load up a cart with bricks or something like that, right? And a human being could pull that, maybe on a frictionless surface with a cart, and I don't know, right? Because of the friction, blah, blah, blah. It seems kind of hard. But if a human being, better yet than pulling a cart, what if a human being could lift straight up 550 pounds through a distance of 1 foot in 1 second? Possible, not possible? Possible. For Olympians, right, in the clean and jerk, right? And right, they're holding those big weights and the bars bending down like this, right? Okay. I'm talking normal human beings.
Wouldn't we just have to generate 746 watts? So move something like a bicycle?
Per second. Right? Right? 746 joules of energy every second. Right? So that's 7.5 incandescent light bulbs burning. Right? Is the human being capable? So I am certainly not capable of lifting 550 pounds. If I did that, my spine would explode, right? So can we game the system a little bit? Instead of 550 pounds through 1 foot in 1 second, what about 225 pounds through 2 feet in 1 second. Is that the same thing? Or 112.5 pounds through 4 feet. See what's happening there? We can change the weight and change the distance as long as we end up with 550 pounds or pound-feet in 1 second. And now it's sounding a little bit more possible. What?
About 1,100 pounds on top of it.
You could do that too, right? But I'm not lifting 1,100 pounds. So, the way that we are going to measure power today is this. I need 37 volunteers. Okay? So each of you, right? Each of you is going to do something. Okay? And if you don't volunteer for the first 9 roles, you're going to default, okay, to that of data taker, writing down the data that we are about to go get. Okay? So there are 9 sort of specific roles, and then there are other, right? So I need at least 3, we'll take some more if we have more. I need at least 3 people who are willing to have their horsepower measured, okay, before you volunteer, right, okay? How are we going to do this? What we're going to do is rather than have you lift weights or do anything like that, we're going to go out to these stairs out here, and we're going to have you run up the stairs. What does this look like? That person's disconnected from the road. Okay, so running up the stairs. What are you working against? What's the force that you work against if you run up the stairs? Gravity, right? So what is the force of gravity acting on this person? It's their mass, right? Times 9. It's their weight. So in running up the stairs, you'll be working against your weight. So the people that volunteer to run up the stairs, not only have to run up the stairs with everybody watching, you also have to tell us your weight. Okay? It can be approximate. In pounds. We're going to do this all in the horsepower units, right? So we need the weight of the person, and then work. Okay? Remember, work is a force times a distance, isn't it? So we know the force is mg, and it's a dot product. We want everything to line up as much as possible. So what distance matters when we're running up the stairs? Is it the diagonal? Is it the horizontal? Or is it the vertical? Why is it the vertical? Because that's where the direction the force is acting, right? Okay. So we need to get the height of the stairs. In other words, right, a change in potential energy is the result of doing the work of running up the stairs. So we need the height of the stairs. So I need 3 people who are willing to measure the height of the stairs. Any takers? Team measure height of stairs, okay? Easy job. Yeah, you'll find out. And somebody else? Third volunteer? Okay, all right. That way we'll get at least 4 different answers. Okay, so I need 3 people that know how to use the stopwatch app on their phone. I need 3 people who can time the runners. Okay? 1, 2, 3 back there. Okay? Right? So you guys know who you are? All right. All right. Who would like to be measured running up the stairs? Show of hands. So, what we got? We got Veer raised his hand. Okay. Can I just do Kush? Okay. How do I spell it? K-H. Do this, right? Okay, got it. King. Okay, I don't want to get too gender specific, but we need the other half. No takers? No willingness? Oh, Frankie, thank you. Anyone else dying absolutely has to know if you can achieve a horsepower or not? Jonathan, you want to do it? Okay. Jon, right?
Yeah.
All right, so here are the people that we are going to have running up the stairs. I've got my 3 timers, right? Meet me at a certain location I'll tell you about in a second. Okay? And I've got the 3 people who are ready to measure. Okay, so what I'm going to do, the rest of you, if you don't have an assignment, are going to bring a paper, phone, something to record data with, right? Because we need to write down the numbers that we're going to get. We are going to go to the stairs that are right out here, right? The stairs coming up, okay? It's not a good spot because it's kind of a tight fit at the top of the stairs. So some of you can go down to sort of the middle landing down there, right? And some of us will be up at the top. I'm going to lock these doors right here so you can leave your stuff right in here. These doors will be locked. Nobody can mess with it, right? And I'll unlock them for us to get back in. So everybody, let's go out there. Bring a jacket. It's cold. Alright, let's see. Alright. So, let's see. For the height of the stairs, what did you find?
Roughly 7 feet.
Roughly 7 feet. You're an engineering major? 7.0 something? So we'll just say 7 feet. Yeah, it's physics. 7 feet is good. Okay? And thank you for measuring it in imperial units because we are working in imperial units, right? You can measure it in centimeters and we can convert it, but the meter stick did have inches on it, right? So, okay, and you did that the easy way, I hope.
Yeah.
By guessing?
Yeah.
No, you measured one step and then counted the step?
Yeah.
All right, so we know the height of the stairs is 7 feet. Okay, so if we're going to calculate this power, right, it's work over time, and the work is mgh, right, all over that time. But the mg we know as weight, right? And we will do that weight in pounds. We're then going to multiply by 7 feet. Okay. Again, I don't have to put little g in there because pounds is not a mass, right? Pounds is the force of gravity, so we got the force. Multiply by 7 feet. And then we're going to divide by the time in seconds. But we do want to get this in horsepower, right? This would get us feet pounds per second. So what's the conversion between feet pounds per second and horsepower? 550 feet pounds per second for every horsepower, right? So to get the units to work out right, in the denominator I would have 550 feet times pounds per second, because that's pretty much what I've got here, right? I got to cancel the feet, I got to cancel the pounds, and I got to cancel the second. Foot pounds per second per horsepower, which would flip that up into the top and give me the horsepower, right? I was trying to put it all into one thing. So for every person, we need to know their weight, multiply that by 7, and divide by their time times 550. For almost all of you who have TI calculators, be very careful with your parentheses, right? Okay. Make sure that you have parentheses around the bottom. Okay, so on and so forth. All right. So let's get the data here. We'll do weight, and then we'll do time. So Veer, how much do you weigh in pounds?
180.
180. Kush?
156.
156. King?
160.
160. Frankie?
145.
145. Jonathan?
195.
195. And Mr. Balogh weighs 4,370 pounds. All right. Veer's time. Kush,
2.45.
King,
3.19.
Ricky,
2.37.
and Jonathan.
2.18.
And Mr. Balog's time was what? 0.13? Yeah, okay. Thought I got that right. So, what we're gonna do, okay, this is what you're gonna do, okay? You're gonna pick somebody from the list, okay? Not just beer, right? You're going to turn to the people next to you and tell them what you picked. And then you're gonna all change so that all of you are different. Does that make sense? So I don't want everybody just calculating kings, right? Try it, we want to so turn to the people around you, say, I'm doing this one, and then, you know, round robin it until everybody's calculating something different. Go!
My hands are feeling.
Alright, we got everybody calculated? You guys figure out how to turn your calculators on this morning? Good start. Alright, does anybody have a number for Veer?
1.018.
1.018? So 1.02? 1.02 what? Alright, for Kush? Point 81. Okay, alright, not bad. What happened there? We're not, no personal attack, right? Physics only, right? So, Kush weighs less than Veer, right? Too late, but thank you. Couldn't find stopwatches this morning. So Kush weighs less, right? So less work, right? Going up the stairs, but did it in a longer time, right? So the power dropped. Now, given a few more chances, could Kush do a horsepower? Absolutely, no problem. All right, King, what's King's? I'm guessing less than 0.8.
0.638.
Okay, 6.3, right? Okay, again, time was longer, right? So the power output was less, right? It was approximately the same amount of work. They weigh almost the same, right? But longer time. All right, for Frankie?
About 0.78.
0.78. For Jonathan? What? 1.13? Jonathan has the shortest time and the greatest weight, right? So that power output, that's right, do you lift? All right. All right, I hope nobody calculated this because I'm lying through my teeth, right? Okay, but you can see I was going for lots of work in a very short amount of time, okay? So as of last night, I was 169 pounds, okay? And my time, I think it was like 2.1, was that the middle one? 1.88? Yeah. Was it really?
That's what I got.
Yeah. As I said, any body part. So, but 1.88? Oh. Okay, I used 2.1, but okay.
Your hand was way up.
750, 1.88. Sorry, Jonathan. But I'm a pro. Are human beings capable of a horsepower? Absolutely. Okay? Every human being is certainly capable of horsepower. Give any of these people, right, another chance, right? Perfect the technique. You just, basically, you have to get up faster, right? There isn't really any way to change your weight. So, story time. I did this exact thing in my Physics 4A class, except it was part of a lab that we had on energy and power. We don't have the equipment here to do it, but part of our lab was, okay, so backstory. My physics teacher, my Physics 4A teacher at my community college was a professional beach volleyball player. She was very annoying because not only is she a doctorate in physics, but she kept telling all of us nerds that we had to go out and exercise. We were really good at exercising our video game skills, but actual physical exercise was something strange to us. Anyway, so she told the class, everybody had to run the stairs. There was no opting out here, okay? Everybody had to run the stairs. And my science building, my community college was 3 stories tall. Okay? So we had to run the stairs, right? Kind of like out here, right? And we had to run the entire length of the height of the stairs. Like can we just do the little, no, all of it, right? She wanted to see us swim. And she was an amazing teacher. She was probably 70% of the reason I became a physicist. Anyway, we had to do like 3 runs up the stairs, right? And I, just had my inhaler and gasped like a fish the whole time. And I remember there was one guy in our class. To this day, I cannot remember his name. I wish I could remember his name. But we'll call him Charles. Charles was not like us, okay? Everybody in that room could do math and all that kind of stuff, but Charles, he could do math. He was amazing, right? The other thing about Charles that was strange about him is that he was on the football team. So not only could he, was his mind amazing, right? But he could take anybody out, right? He was fast. He was built, right? He wasn't like a linebacker or anything like that. He was a receiver, but he was in shape, okay? The other distinguishing thing is that he had a girlfriend. Anyway, Charles got it into his head that he had to achieve 2 horsepower. That was his goal. And the annoying thing is that he ran up the stairs 10 times, right? Every time getting faster. And super annoying, he never seemed to be out of breath, right? He just, right? We're sitting there trying to time him. We're like, wait, we need to reset. He was getting 1.7-ish, right? Around that. He was kind of peaking out of one. And we had all gone back inside. We were doing calculations as part of the other lab. And he came in and he shouted across the room, "Hey, Balogh, come here." I'm like, oh my gosh. So I go over, I'm like, yes, Charles. And he said, I need your help. I need to get 2 horsepower, right? And I'm as fast as I possibly can be running up the stairs. I need more weight. And he had called me over because I worked in the back room as a student helper, and so I kind of knew where all the stuff was. He said, "Do you have any weights that I could carry up the stairs?" And I was like, well, yeah. We had a box of bowling balls, right? And so I grabbed several bowling balls, and we borrowed people's backpacks. We got to empty out the backpacks and put 2 bowling balls in each backpack, right? And he wore 3 or 4 backpacks. He put 2 on the back and 2 on the front, right? And ran up the stairs, right? Okay, and he got 1.87 something, right? It slowed him down a bit and all that kind of stuff. And we're like, okay, have fun. We went back. So about 3 minutes later, he comes in. He's like, Balogh, come here. We don't, there's no more bowling balls, right? Okay? And we don't have lead bricks or anything. He's like, here. He hands me a bag full of bowling balls. He said, put this on. I was like, dude, I've got my 1 horsepower. I'm happy, right? I don't want to run up the stairs. He says, no, you don't understand. I want to carry you up the stairs. What? He's like, please, will you just ride piggyback as I run up the stairs? Will you just put a couple of these backpacks on, and with your weight, I think I can do it. I was like, no. This is stupid. It's like, come on. Fearing for my life. It was either die running up the stairs or die in a dark alley somewhere. And, no, Charles is a nice guy. He'd never do that. But I was like, oh, okay, fine. I was the smallest guy, right, in the room. So, like, I was the natural fit. Anybody else would have been just too lanky or too many parts going there. And so I was like, okay, fine. So we went outside and got to the bottom of the stairs. I was like, okay, so how is this going to work? He says, well, I need my hands to pull on the stair rails, right? So I can't, like, hold you up, right? So you just have to climb on my back, right? Wrap your legs around my waist. Wrap your arms around my neck and just hold on. Can you do that for me? I was like, sure. And I was like, but wait a second. If I wrap my arms around your neck, how are you going to breathe? He said, don't worry about it. Fair. So that's what I did to this day. I remember the horror of it. Okay? Because I couldn't see anything. Okay? So I climbed on his back, put my arms around his neck, right? And shut my eyes and screamed all the way up the stairs, right? He got like 2.1 something horsepower. Like it was pretty big. I think we shortened the distance. I don't think we did all 3 levels of the building, but yeah, I've never. That was the closest I had come to death in a physics lab situation. The point is, right, that human beings can definitely achieve a horsepower. And as a matter of fact, I've committed to, if this number ever drops below 1, I need to think about retiring, right? I'm getting to the point, right, where I'm old enough that it's not going to happen anymore. But I think we probably need to answer the question, what's the difference between you and a horse? Well, let's not be so personal. What's the difference between a human being and a horse? Obvious anatomical differences aside, right? Okay. What can a horse do?
Use all 4 limbs.
They can run longer distances.
It can do 1 horsepower all day long, right? If you ask a human being to do a horsepower all day long, what happens? Death is what happens, okay? Human beings, we evolved not to like really kind of sprint, right? We can do the initial sprint to get away from the tiger in the grass, right? But really our main thing, our survival technique is run farther than the lion, right? Get out of range. So we're better built for long distance stuff than we are for instantaneous power. A horse, give it some oats and some alfalfa, it's happy, right? It'll just do a horsepower all day long, right? Okay? Human beings, you ask them to do a horsepower, like, what? Not gonna do it. So, there you go. And the promised field trip is taken. All right, transitioning back now.
Where was the original destination?
It was the back stairs. Out there. Yeah, it wasn't. Told you not to get excited. All right. Let's do a couple more of these examples, and we'll be finished with that. So switching back into work energy, right? The conservation of energy. What I would like you to do, okay, is right now with each other for the next 3 or 4 minutes, I want you to set this up, right? And specifically talk about where you're going to put initial, where you're going to put final, and where you're going to put 0. So, go.
think N would be like the 0, right?
And 11. Oh, finally.
Let's call it that.
Well, I hear a lot of talking. I know you're sort of absorbing the questions. But you kind of start right away, like, hey, where are you going to put this? Where are you going to put that?
Yeah. They basically told us what
All right, how'd you do here? Were you okay with the wording? Usually when they say a hill is this far, this long, right? They're talking about the diagonal. Okay? What kind of words will they use to talk about the height of the hill? Tall, height, right? Peak. They'll refer to like a vertical distance more specifically. But if you're just told the hill is 15 meters, okay, it can be a little bit confusing. Usually that's the diagonal. Okay? All right, so good there. Where did you decide to put initial? Right at the top, right? Because that's where they start. And where did you put final? Okay, so they're asking us to go for an amount of work that's been done. Because, sort of implied that that's the amount of work across, down the entire hill, right? And you're used to whatever a hill is drawn as a triangle, right? Okay. So where did you put 0 for gravitational potential energy? At the bottom, good. Are there any springs here that we need to worry about? No. All right. So we start with work other plus energy initial equals energy final. Is there work other in this problem? Oh yeah, because we're being asked to find it, number 1. Okay. Number 2, there's actually 2 work others. What's one of them? The constant friction, right, that we're told about the problem. So they're sort of combining here, right? The friction in the wheel axle and the air resistance, right? Okay, they're giving us this sort of average thing. So we do have work from the resistance. Okay? What's the other source of work? Of work other? It's the push, right? Remember, anything that's not gravity or a spring. ends up in work other. Any other forces, anything that's adding energy to the system. And as the boy grabs the wheels and pulls on the wheels, is that energy being added to the system? Or energy being taken away if it were friction, right? These other things that are going on that aren't gravity, aren't springs, they always end up in this work other term. And it's more like a sum, right? You're adding up all of that, these other things that we don't really know how to deal with, okay? So we've got work by the boy. Those are the two forms of work other. All right, energy initial. What kind of energy does the boy have right up there at the top? There is gravitational potential energy, is there not? So I'm just going to write mgh. Any other kinds of energy up there at the top? Kinetic. Why does the boy have kinetic? He's moving, right? So it's 1/2 mv initial squared. Any other forms of energy? Any springs up there? No. I mean, the good news is there can only be 3, right?
Yeah.
It's either going to be mgh, or it's going to be 1/2 mv squared, or it's going to be 1/2 kx squared. Right? And you know the questions now, right? Is it above 0? That's for gravitational potential energy. Is it moving? That's for kinetic energy. And is the spring compressed or stretched? That would be spring potential energy. Okay, same questions at the bottom, right? Is it above or below 0? At the bottom. No, it's at 0. So there's no gravitational potential energy. Is the boy moving? Yes. Right? We're given the speed down there, so it's going to have a 1/2 mv final squared. Okay? And are there any springs down there? No. Right? So there we go. Right? I covered all the bases. And now, what are we being asked to solve for? Work by the boy. So just to be clear, right? This part right here, here's our energy initial. Here's our energy final. And then this was the work other. Right? Those two things right there. Okay, so we are solving for work done by the boy. That's what we're after, right? Before we can, so do we know what MGH is? Yeah. Okay, we're given all those, that's a number. Do we know what 1/2 mv initial squared is? That's again all of a number. Do we know 1/2 mv final squared? All a number. Okay. So those are just numbers. We can put them in when we want or move them around, do whatever we want, okay? The only other thing we're sort of not sure of is this work done by the resistance. So how are we going to find the work done by the resistance? Do they give me the work? It says the resistance can be modeled as a constant frictional force. So how do we find work if we know a force? Force times distance, right? But we got to remember something. It's friction. So what kind of work is this kinetic friction doing? Negative. Ooh, not green. Negative force done by the resistance times the distance that it goes, right? And what are we going to put in for that distance? Yeah, this is the 12.4 meters, right? And then we solve this thing for work done by the boy. I could write all this down, or I could have just moved stuff around. Work boy is going to be equal to 1/2 m v final squared minus v initial squared. Make sure to not square the difference. Make sure to square each thing and then subtract them. That was several algebra steps where I moved 1/2 mv initial over to the other side, which picked up a minus sign, and then I factored out the 1/2 m. Minus mgh plus force resistance times d. And then you can go in and throw in a bunch of numbers, and you get 168 joules for those of you that were curious about the numerical answer to that one. I don't apologize for doing algebra very, very fast, because I'm A, not a math teacher, and B, don't like math.
What was your initial speed and final speed?
What's that?
Your initial speed and final speed?
It's 1.4 at the crest of the slope.
Oh, okay.
Second line right there, and then he's going 6.2 at the bottom.
Okay, I didn't see the one.
Yeah, it's right, it's hiding up there on the side. So, just showing you there, right, that work other term can have both positive and negative things to it, right? The boy's adding energy to the system. The air resistance is taking it away. Air resistance is negative work. And also one of the things I watch students do a lot of is overcomplicate the problem. If you're asked for work, don't put in force boy, distance boy, right? You can find the force the average force that the boy did. But now that we know the work, how do we find the force that the boy applied? Divide by distance, and you're done, right? Like, so if you're asked for work, just leave it as W, like work done by whatever, right? Everything else will work out. If you write force times distance, you might end up solving for the force, and Wiley plus will give you the red box because what it wants is work, not the force. So be conscious, right? You don't always change a work into force times distance. Sometimes it's just work, and you're solving for the work. All right. Let's go to this next example. Let's lower the light. A little bit of physics mood light. Oh.
Raising a mass increases its gravitational potential energy.
You don't say.
We'll use this triple track to show that this energy is conserved as it changes from one form to
Does he
another.
look excited?
We'll release a rubber ball down each of these 3 tracks. Each track has a similar downhill section, but the uphill sides have different slopes. If a ball is released from the top of each track, how high will it rise on the other side in each case?
Okay, we're not going to formalize this as a quiz, but just turn to each other, right, and answer that question. He's going to run the ball down each of the tracks one at a time. Where does the ball go the highest on the other side? Go.
Do you have any different tiles machines in here? It's a little bit complicated. I don't think it's mostly on the chair. You'll think okay.
The only difference is the angle of elevation. So could we say that less triangle, there's less of that
All right. So, what's the answer?
The first one.
Just the first one? They're equal? Why are they all the same? Energy's conserved, right? If they all leave at the same height, they're all going to end up at the same height regardless of how long the slope is. All right, so let's see if that's true. You look so serious. Right?
Here's the ball rolling down the first track.
Okay. All right, be careful. If you don't do this right, we fire you. Ooh, ooh.
The second track.
So why is he being so careful? He doesn't want to give it any initial kinetic energy, right?
The third track. The ball rises to the same height from which it was released in each case.
So the last one was a little bit short. There's a little bit of friction in the system, right? Okay. You can see it because the ball didn't roll back to exactly the same height. But anyway, it's close to the same as the real world can get. Yeah, some of you are like, good thing that was not a quiz. All right, last example. So, again, I pulled a Mr. Balogh here, a physics thing, and everything in quotes, it'd be a number that would be given you, except quite possibly, yeah, the distance d, okay? The distance the spring compresses, okay? Sorry, distance x. I shouldn't put quotes around the x. But I did want to set it apart from everything else, okay? Maybe we'll do this. Sorry, 1 second. Real-time edits. There we go. I don't know what you're talking about. There's no quotes around the x. All right. So, got to absorb the question, right? Is there a spring in this problem? Yes. So does that mean instant panic? Yes. Right? But it's okay. We have the tools. We can do this. So let's get a drawing, right? Okay. And some of you have encountered these problems on your homework already. So the object is sliding along, right? Okay, moving at some speed v. When it hits this rough patch, okay, where there is friction, and they give us the coefficient. What kind of friction will it be? It's kinetic sliding, right? Okay, so there's going to be work done by friction there. It's going to take some energy away from the system, and then after that, right? It runs into a spring, okay, and like compresses that spring, right? So where do we put the 0 for a spring always? At its resting point, at its equilibrium position, at the position the spring would have when nothing is touching it. So that'll be there, and then like it'll compress, right? It's kind of hard to draw some of these things, right? Okay, but it'll compress some distance x, right? What else have they told me? They told me the mass of the object. That's good, okay. We know it starts with v naught, okay. We know that the distance across this patch is d, right, with a coefficient mu. They gave us the spring constant k, right? So we're after x, and it's our job to set this up, right, in such a way that we include the spring potential energy, because that's where the x is going to show up, as well as take care of everything else that's in the problem. All right. So we need a 0 for gravitational potential energy? Yes, no? Sure? Where would we put 0 for gravitational potential energy in this problem? On the ground, right? Lowest point of the problem. But is there any change in gravitational potential energy? No. How much gravitational potential energy does it start with? 0. Well, how much does it end with? 0, because it was on a flat surface, right? It didn't do anything. So we really don't have to worry about gravity in this problem. So let's see here. Where's the initial point? On the moon? Mars? My driveway? Where's the initial point? Oh, like where it hits the rough patch? Great, okay, because really kind of anything, like you can put it there, you can put it there. The point is, before that rough patch, it's just going to be moving with whatever speed it has, right? There's nothing going on. So we'll do right as it hits the rough patch. I like it. Put the initial point right there. And then where's our final point going to be? When it compresses all the way. Because we're looking for something there, right? We're looking for the total compression of the spring. All right, so we got 0 for the spring. That one's sort of, we can't pick that one. That's picked for us. We got 0 for gravity. We're good. All right, so we write down an equation. Work other plus energy initial equals energy final. It's where it always starts. And you ask yourself the questions. Do I have work being done by something that's not gravity and not a spring? Yes or no? Yes. What is that work? It's the work done by the friction, right? So you could go just work sub friction right now if you wanted to, or typically what I do is minus F times D. right? Just to show that it's the work being done by friction. Unless they're just asking me for the work done by friction, in which case I just leave it as W. All right, no other work others. Initial energy, what kind of energy does it have at the initial point? It's all kinetic, 1/2 mv naught squared. And then at the end, what kind of energy does it have? It's all spring, right? Comes to a stop. It's just 1/2 k x squared. So let's see here, solving this for x. Okay. So I know k, I know 1/2, I know v naught, I know the mass, I know 1/2, I know d. I don't know f. How do I find the force of friction? Fun. True story. I was at a dinner with some friends on Saturday, and their son, mechanical engineering graduate working for Ford, helping design cars, trucks, and things for Ford, was also, well, before he had 2 kids, was into drifting, okay, and in drifted cars and competition circuit, all that kind of stuff. And we got to talking, and he said, "You're a physicist, I have to ask this question. I've never had this question answered before." It's like, okay, go ahead. I thought it was going to be like quantum mechanics, weirdness, Schrodinger's cat, blah, blah, blah. That's usually the kind of questions I get. He's like, the coefficient of friction. I used to drift cars, right? How does like that really work? I was like, you're a mechanical engineer, right? He's like, yeah. I know how to like design cars, I know traction systems, like all that. But we're always just sort of taught that it's just the coefficient and just go with it. Like, seriously, what's going on, right? And we proceeded to have a 25-minute discussion about atoms and molecules, and right? And he had it was interesting, he had all of this language from his career in drifting to talk about how the tire would grab the surface. They had, I can't remember the terms he used, but they had a word for how the drifters are just, they're psychotic about the patch, about the contact point between the tire and the road, because that's where everything is happening. And a drifter is like trying to go between kinetic and static friction almost constantly, right? To get the car to do its tricks. And he talked about having like, he said there was a way that the tire grabs towards the inside, and then there's a way the tire grabs along the axis of the car. And anyway, you never know where fun is going to crop up, right? Even on weekends when you thought you were safe. Anyway, no, it was a really fun discussion. We really geeked out, and the rest of the table ignored us. All right, which was fine with me. Where was I? Oh, fun. It's going to be mu. Okay, so what do we put in for n for the normal force here? Yeah, since it's just flat, we can just go ahead and put in mg because the object isn't accelerating in the vertical direction, right? So it's mu times mg, that would be my f. So I put that in over there, times d, 1/2 mv naught squared equals 1/2. Can I just cancel my m's? No. That's a fun mistake to see on an exam, right? You're in the thick of it, you're rocking it, the flow's happening, and you're like, oh yes, M. And then you realize there wasn't an M in one of the terms. I have a tendency to overlook things like that. You get the minus sign wrong, I'll come after you. All right, what are we solving for x here? So let's see, I'm going to multiply everything by 2 and divide by k. So negative 2 mu mgd over k plus mv naught squared over k equals x squared. So that means x must be equal to the square root of m over k, just factoring some stuff out, v naught squared minus 2 mu g C, that's supposed to be G right there. Again, I did some algebra really fast there. You probably don't want to do algebra that fast. Otherwise, bad things happen. On your homework, you're going to have similar problems, but they're going to be at angles. Okay? Matter of fact, we should probably just start driving into the homework with the last 10 minutes that we have here. Some of the chapter 8 homeworks and kind of how to navigate through those. Pull that up. Not chapter 9 homework. Good. Go to student view and then turn everything on. There. So the conceptuals, I'll let you suffer through those. Okay. You know what? Let's go in reverse order. Because that sounds fun. Okay. What's going on in this one? Aha! Okay. This problem, annoyingly, is making you break up the problem. Because in part A, where are you asked to find something? Like, where in the problem is it asking you to find something? At the bottom of the hill, right? So you can just do a work energy. There's friction along it. So with the fact that the hill is, the ramp is tilted, right? And there's coefficient on there, like I just mentioned, right? Is the normal force equal to mg? What's it equal to? It's mg cosine theta, right? We got to get the component. We got to get the exactly opposite what n is. So n equals equal to mg cosine theta, right? So you then solve for how fast it's going down here at the bottom, right? So that's part A. And then to do part B, you basically set up a new problem, right? Because it's along the floor, okay? So the final from part A becomes the initial for part B. So on and so forth. You could go back to the top of the hill and do it all the way from the top if you wanted to. But they're kind of annoyingly keeping that the same. Okay. Do the answers A and B increase, decrease, remain the same if we have the mass of the crate? Well, how do you know if it's going to depend on the mass? Yeah, if you're doing the setup and you leave it symbolically and the mass cancels out, does it matter what the mass of the crate is? No. I would just do physics to answer that question. That wasn't one of the button. That one. Go backwards. Okay. Oh! It just looks bad, doesn't it? It just looks like it just, Mr. Balogh, what are you doing to me? Why? This will never happen in my life. Never say never. Again, sort of annoyingly, they're forcing you to do the problem several times. What's happening, how fast is it going at B, C, D, right? All these different things, right? Nice thing about B and C, no friction yet, right? It's a little bit easier. Let's go for D here. In all three cases, where would you put 0 for gravitational potential energy? The answer is it really doesn't matter, but following Mr. Balogh's advice, right down here, okay? Especially since they're giving like H1 and H2 referenced from that lowest point in the problem, okay? This just, if you put like 0 at A, well, you got a problem. If you put 0 at C or D, which seems sort of natural, like at point C, why wouldn't I just put 0 there? that actually works really well. It does. Okay? You just gotta, again, have to be careful about how you're referencing things. But if you put 0 at C or D and you try to solve for B, it can be a real problem. So yeah, I'll leave it up to you. It works either way as long as you're careful. But when it comes to finding it for part D, okay, first of all, the question posits something very interesting. Does it make it? Right? Does it reach point D? If it does, how fast is it going? Right? And if not, how far? So how do you determine whether or not it makes it? It's very simple. You go down, because it's Wiley plus, you pick a unit, you hit submit, and if it's not a distance and it is a velocity, what do you now know? Okay, but you just did an end run around physics, right? You gamed the system because they give you unlimited try, right? Which is fine, right? It's not a problem. But it's on you, it's your responsibility to make sure you know how to figure this out. So assuming we didn't have red and green boxes, right? And it was just the problem, how would you determine if this thing actually makes it all the way along the friction part? What do you have to do? So, you make an assumption. You say, I'm going to assume it does make it through the entire friction section with velocity to spare, like it's still moving, right? And so you're going to set up the problem to solve for the velocity it has at the end of that distance L. If it's impossible for that thing to make it through that entire section, and you try to solve for the speed that it has at the end of that section, what's going to happen? You're going to get negatives under square roots. You're going to get an answer that doesn't make sense. It's just going to blow up on you. And I'm not saying it's going to blow up you like algebra usually blows up on you. I'm just going to say like you've set it up, you've done it right, and you're getting imaginary numbers, right? Now you know that it doesn't make it, and then you go back and solve for the distance, right? Assuming that the final, because if it doesn't make it, how fast is it going? 0, right? It comes to a stop. So the other choice, you don't have to choose that it has speed. You could choose, right, the final speed to be 0 and solve for the distance that it slides in that rough patch. So let's say that distance L, did they give us a distance? 13 meters, right? So let's say we assume it comes to a stop. We're going to set the final speed equal to 0. That's kind of nice because it wipes out the kinetic energy at the end, right? You get a 0 term. Okay, great. So I solve for that distance, and I get 15 meters for my distance. What do I now know? It didn't stop, right? If I get a distance again, if I get 10 meters, then I'm done with the problem. But if I get something again that doesn't make physical sense, I know that it did make it, and I have to go back and solve. So that's part of the problem-solving process that engineers run into all the time. You don't know what the outcome is going to be, so you assume an outcome, you solve the problem, and see if your answer makes physical sense. If it does, then it's likely that that outcome is going to happen. If it doesn't, something else is going on. All right. Let's see. Wow. Right? Just fun. There's an angle. So fun. What's the normal force going to be? Mg cosine theta, right? Again, if the devilish if, right? Okay. It's one of the things I hate in computer science. If then else. If it can make it, so you're being asked, right, again, to determine. Does it make it? Does it not make it? So you're going to have to make an assumption, right? And of course, you can trick Wiley Plus into telling you what it is, okay? But do the due diligence to like, okay, I'm going to assume it does come to a stop. So I'm going to find the distance that it slides, right? And if you find it's too long, go back and find the velocity. Where would you put initial? Probably down here, because they tell you how fast it's going down here, right? Okay. Final. This height, they give you a height up to this portion right here, and they give you an angle, right? So you're there's gonna be some trig involved in the rough patch area to get the hypotenuse, right, and the change in gravitational potential energy in the rough patch. So trig alert. The last one's harder. This one's the easier version of it, right? Matter of fact, it tells you that it stops, right? So anyway, we just have to find out what the distance is. Same thing. Does this little dippy part matter? No. Not at all. Right? And where would you put 0? You could put it down here, but do you know any information down here? No. So where's the next best place to put it? At that line that they drew for us, right? Okay, because they did give us that height difference, right? All right. Skiers are happy right now, aren't they? People that live in the mountains not happy. Skiers very happy. I have a friend that does ski patrol up at China Peak, and he's just grinning. Okay. By how much is the mechanical energy of the skier system reduced because of air drag? That is very definitely a physics sentence, isn't it? So let's translate. We need Google Translate. I wonder if Google Translate could do this for us. They're asking for how much work was done by air drag. They couldn't ask a simple question, right? Okay, because the work done by air drag is the energy that was taken out of the system. That is the work other, right? It's lost in the sense that it's not mechanical energy anymore. And we've been very narrowly focusing on kinetic and potential energies, right? Work other is a way for us to handle everything else. So in this question, just remember, by how much mechanical, they're asking for the work. Not the force, not the distance, just that term. And that term will be the difference in kinetic and gravitational potential energies. If there were no air friction, then the amount of potential energy the skier had would be exactly equal to the amount of kinetic energy and potential energy at the end, right? They would equal out. Here, they're not the same. The initial and final energies are not the same, and so the difference in those energies is the work. In another way, right, to look at this equation is to move the energy initial over here, right? If there's no work other, if work other is 0, then the amount of energy you start with and the amount of energy you end with is the same. It's the only way to get 0, right? If the difference between these things is not 0, where did the energy come from, or where did it go? Converted to work by something else. A lot of ways to write that are all the same. Ah! Okay, so there's a spring. So 1 half kx squared?
Is this going to be on the exam?
Sure.
It's a lot to do the homework and the exam and study.
Yeah. You're right. You're asking me to push the exam back 1 week?
Low key.
Passive aggressive way. I'm not going to do that. You can do it, right? And in fairness, I've been warning you that Chapter 8 homework being due comes up quick because it comes up on Wednesday. This always happens right the week before the test. So yeah, it's brutal. You'll make it. You'll be okay. There's a lot, isn't there? Newton's second law, we could have tested just on that, right? The good news is because both of these things are on there, and it's only 2 hours long, that kind of limits what I can ask you, right? Okay? So take comfort in that. Yeah, all the keys are available except for the key for decorating. Just go back to the old assignments and the solution button is right there. I'll see you on Wednesday. Come with your questions.